Tuesday, we got 4 classes left, today, Thursday, and the next week. The plan for this last stretch is to talk about some science and then do some science. So today, I'll tell you about the Lorenz Equations and some experiments that I've been involved with related to them. And then on Thursday, there's going to be a special guest lecture by Jim Bogro, who is a faculty member in math and complex systems. And he's doing all kinds of interesting work related to dynamics on networks, in particular social networks, but other types of networks too. And then a week from today, we'll come back and I'll finish up with some. So the Lorenz equations are talked about in Chapter 9 of your book. So we'll talk a little bit more about other topics in Chapter 9. And then a week from Thursday, you'll turn in homework 12, which I'll put up this Thursday. And we'll do an experiment over in Voti. And I'll give you the take-home final. And then that will be due whenever the final exam period for this class is, which I think is the following week. Okay, if it starts 7, I won't have you come at 7:30 to turn it in, but maybe if it ends at 10 something, then that would be a good time to have it in by on that day. Or the day before. That would be fine too. That's the plan for the next couple weeks. Does anyone have questions? Yes? Yeah, you could just slide it under my door if I'm not there, or come, yeah, if I am there. Yep, that's fine. If you want to turn it in early, yep. Other questions or comments? Okay, so I have a bunch of random things to talk about first. One is that I did my first bike race this weekend, and I survived. It was Rasputitsa, and I'm going to show you a couple pictures of what it's like. So it was a race around Burke Mountain in the Northeast Kingdom, and it was still quite cold. It was like upper 30s, raining, and a lot of snow. So my son decided he got the GoPro for Christmas, remember? And so he said, you should put this on your bike and it would be fun. I wasn't going to do it because I figured you'd get covered in mud. But there's sort of like gravel and mud roads that you're riding on. I'm not competitive. I'm sort of like middle of the pack. Some people are done and really quickly, but sort of some muddy stuff going on, which was kind of fun. There were plenty of UVM cycling types there, I think, too. I didn't really see them because they're faster. But it's all, through a bunch of farms, and, like we went past this guy's farm, and I think he like specifically brought a bunch of mud into the road, and he's there like cheering us on. He was excited to see us. That was cool. There's a section called Siberia that's like a 15% grade that's all like snow and ice and like muddy ruts and things like that, and so that was non-trivial. And then this is the big finish. So this was like it took me almost 3 hours. The winners did this in like 2 hours. So, I was lucky not to fall there because I was so, like, there's a lot of cramping going on, and, it was pretty fun. So those are my friends who I did this race with. Some of you will know Ben Emery. So he did really well. He was there. He's a grad student in math now. So that's fun. I'm excited to do that again sometime. So that's one random thing. Another thing is this cool commercial, this paint commercial by Sherwin-Williams, which I'm going to show you because it's pretty awesome. Let's see if I can get it to work. So that was all real. There's no CGI there. They have this amazing like little experimental fluid tank where they're injecting the paints, and then they have a robotic camera that they can move very quickly, very precisely through the fluid to watch what happens when the injection goes in. And so there's a link. I tweeted this, but there's a link to sort of a how-to about how they did all this that's also very interesting. being able to simulate that, like what happens when you have two fluids of different densities and they're moving relative to each other, is basically like impossible. So it's just to give you a sense for how difficult some of the problems that people are working on in this area. Certainly the statistics of what's going on, that sort of thing, like the sort of properties of the dynamics that you observe, the scales on which things are happening, that sort of stuff, people have a good handle on. But simulating actually what happens is quite difficult. So very cool stuff going on there. I will have office hours this week from 9 to 11:45. That's tomorrow. So you're working on homework 11, bless you, if I'm right. So that'll be due on Thursday. And as usual, you can come and hang out and work on it if you want. There'll be other people there doing that. You can come and ask questions. All right, so that's happening. And let's see. So the topic for today is the Lorenz equations. And I'm going to I'll have lots to say about this, but I just want to give you a sense for the thing that's going on. We're going to talk about an experiment that's meant to simulate convection. So you've heard the word convection. It's the process that happens when a fluid or a material or the air, what have you, is heated from below and cooled from above. The warm stuff wants to rise, the cold stuff wants to sink, and then you get these interesting flow patterns. Mainly this sort of, the dominant pattern is the warm stuff rises, the cold stuff sinks, and you get these big convection cells. They're responsible for thunderstorms and your plane being late. Things like, there's a lot of consequences of convection. It's something that people try really hard to be able to model well, certainly in the atmosphere, with respect to understanding the climate and doing weather prediction. People are also interested in it in the Earth's core, because there's convection happening there. There's basically, anytime there's an imbalance in energy, there's convection happening. It's sort of everywhere. One of the simplest experimental versions of this is a hula hoop filled with fluid and differentially heated from below and above. And this is an interesting experiment that I've worked on and that I'm going to show you some simulations of. This is one simulation of what goes on when you heat the bottom half of this hula hoop and cool the top half, and you're trying to see, well, what happens? You're looking at contours of temperature. So the warm stuff on the bottom heats up, the cold stuff on the top cools off, and it's kind of frustrated because the cold stuff wants to sink and the warm stuff wants to rise, but there's nowhere to go because the hula hoop is this symmetric thing. And so interesting things happen. And in this particular case, this is a simulation done by Will Luisos, who, if you're an engineering student, you probably have had as a professor. He did a PhD here and does a lot of fluids research. And so this simulation has millions of locations in the hula hoop that it's trying to decide what the temperature and the velocity and the pressure are, and the speed of motion in 3 dimensions. And it's integrating what are called the Navier-Stokes equations for fluid flow, on this grid with some approximations going on for what happens underneath. And what you can see is what happened while I was talking is it sort of picked counterclockwise as the direction it would rotate in. So now you get the cold stuff on the bottom and the warm stuff on the top. And that's not what the forcing is. The forcing wants to cool off the stuff on the top and warm up the stuff on the bottom. And so it doesn't stay like that forever. And so the question is, in this particular case, what happens? What happens when you put a fluid into this environment, you differentially heat it? What sorts of behaviors could you end up observing? This particular simulation you're watching the transient behavior sort of it's spinning up. The model's spinning up to some state. And whatever the state is, you want to analyze aspects of it. You want to know, is it stable? Whatever behavior results, is it a stable thing? So you might imagine that, you heat up the bottom and you cool off the top and nothing happens. It just sits there. And that is what happens if the temperature difference is small. You heat up the bottom half a little bit, you cool off the top a little bit, and sort of conduction is the word you would use to describe all the little molecular motion that's going on that equilibrates the temperature. So it linearly would vary basically near the boundary between the top and the bottom, but no motion. That's conduction. So that's a stable state for this system for small differentials in this forcing. And as you increase that difference, that state becomes unstable. You don't really have to increase it very much. And so that conducting state kind of becomes one of these sort of pendulums standing up. And even if you could get it there, it would leave. And it would pick a direction to rotate in, clockwise or counterclockwise. and it would equilibrate in that motion, in that direction, and a constant velocity forever. Okay, so it would be, that's called steady convection. Turns out that's not, do you have a question? Yeah. Yeah, those circles are cross sections. So this is a fully resolved three-dimensional flow simulation. So if you slice the hula hoop here at 9 o'clock, what does the cross section of temperatures look like? And that's what this is. And here it's at 6 o'clock and 3 o'clock and 12 o'clock. What do the cross sections of temperature look like? And there's a cross section at every time on the clock. It's just hard to look at them all at the same time. So you can do things where you sort of like fix a position and then you could kind of like zoom that through and you could watch what happens. These cross sections are just fixed. But there's different ways to visualize this sort of thing. It's hard to visualize three-dimensional fluid flow. So now it's rotating counterclockwise, right? You get the hot stuff is rising, the cold stuff is sinking. You can't, since this is temperature, you can't quite immediately see what the velocity is, but that's what. So it's still going in this counterclockwise direction. I'll show you some simulations where it's easier to see that. Let's see. Okay, and then so that behavior where it's where the stable behavior is convection in one direction or another, that as you dial up this temperature difference, that becomes unstable, those two states where it's counterclockwise or clockwise rotation. And a new long-term behavior results wherein the fluid will rotate in one direction for a while, speed up, slow down, speed up faster, slow down even more, stop, turn around and go back in the other direction. And do that process aperiodically forever. So it might spend a minute going one direction, and then an hour going in the other direction, and then 17 minutes going back in this way, and how, that aperiodic behavior is what Lorenz's paper in the 1960s was about. So this experiment is a physical realization of the differential equations that Lorenz described the behavior of in this 1963 paper that I talked about on the first day of class, deterministic non-periodic flow, that was later described as chaos by Jim York. So, all right. So this is now a video of an experiment that we worked on here, and that Dave Hammond and Darcy Glenn and a few other people built over in Cook. And let me see if I can kill the sound here. There we go. So let me turn this off as you can see. But there's neutrally buoyant beads in the fluid, and there's a black light, and you can see that it's sort of so it's being heated from below, cooled from above. It's rotating counterclockwise. Now it's going to turn back and rotate clockwise. The inset is, I'll describe later, but it's one way to see which way it's going. Still going clockwise, and it's going to slow down. And turn around, go back counterclockwise once. And stop, turn around. Let's go clockwise for another so often. So this is kind of funny because you think about, well, like, so if we let this go for, 24 hours, if we just let this go, it wouldn't equilibrate. It wouldn't come to a decision that, we're always going to go clockwise. And what's interesting about that is the forcing is constant. It's not like, we're changing the temperature on the boundary and moving that around or modulating it up and down. We're setting the parameter at some fixed value, and the long-term steady state is aperiodic. Which is what this class is about, right? We're trying to learn about why does that happen. And when I first heard about this experiment, I said, no way! Like, how could that possibly happen? There's no way that if the system is contained and there's no external forcings or whatever, that it could continue to show that type of behavior. So we're going to try and decide why that happens today. We'll write some equations down, and I'll talk about Lorenz's model and simulations of it. And you had a question?
Yeah. It seemed like the rotation preferred one direction in longer.
Yes,
Scales.
in that in
longer time scales, would that balance out, or would it prefer one direction or the other?
Good. So your observation is a good one. That in that experimental realization, it looked like it spent more time going in one direction than the other, and that will be the case for any experiment that you build because it's not symmetric. So if it were perfectly symmetric, that conducting state I described, it would never leave that state because it would, everything would just kind of balance out and even go really hot on the bottom and really cold on the top, and they want to move. The forces are equal on both sides, and okay. But practically speaking, and you go and flick the thing, and it would leave and have a direction to rotate in, but that initial choice will depend on small asymmetries in how the heating is happening. So when I first started working on this experiment, I was in college, and I wanted to do a thesis, an undergraduate thesis, and on fluids. And nobody at the school I went to did any fluid stuff. So I called this guy, York, who's the author of your book, and I said, how do I do an experiment that's cool in chaos? And he said, well, you take this tube, go to Home Depot, put it together, and then and wrap the bottom half in heating tape. So I did that. I wrapped the bottom half of this Home Depot plastic tube in heating tape, and when I did that, it was hard to get it so that it would be perfectly symmetric, the amount of heat on the left and the right, and so it was biased to go one direction or another. And there's more to that story that I'll get to in a bit, but okay, other questions? All right, so I said that this is about, so we're talking about, let's write some words on the board. We're talking about chaos in differential equations. And this is chapter 9 in your book. Some of you haven't had a differential equations class, and that's okay. This chapter of the book is not going to require that you solve any differential equations by hand, which is what Math 230 and I guess Math 271 and sort of the differential equations you're typically exposed to as an undergrad. You can write down the solution to them by hand, which really doesn't ever happen in the world. You go out and you see a system you want to model. You can't write the equations down or the behavior as a function of time down. So you do numerical simulations, which is what we're going to do. I'll give you MATLAB code to do that sort of thing for this system. And the idea there is, so in this section is just that we talk about a few of these. The canonical one is the Lorenz equations, which, as I said, resulted from, Lorenz back in the 60s. He wants to figure out how to show the Weather Service that nonlinear behavior is important and the linear stuff they're doing isn't going to work. So he tries to boil down to as simple as possible a model of the atmosphere, in this case convection, that exhibits some of this behavior, which he, at the time he really wasn't sure. He didn't know about the sensitive dependence on initial conditions thing, but that also was a part of this this paper that he wrote. All right, so let's see. So what to say about this? So the idea that Lorenz was working on was, and he had, I'm seeing here, he had 16 kilobytes of RAM on the computer he used to do this, and it would do 60 calculations a second. So that's one of the reasons why, all right, so he's working on this, and the concept at the time was, well, we'll model this two-dimensional convection sort of Rayleigh-Benard cell, where you have a cold plate on the top half of some chamber that's sort of thin, and you have a hot plate on the bottom, and there's then this temperature difference, delta T, across that gap, and you fill it with fluid, and interesting things happen. Vary the geometry by making the plates farther apart from each other, or, you can vary the fluid. You can vary that temperature difference. These are different parameters of a convection cell, of a Rayleigh-Benard convection cell. Okay, and so there's a fluid in here. Gravity's pointing down. And so the idea is, well, what happens when you turn on the juice? Like you turn on the energy here. what happens to the fluid. So we said warm stuff wants to rise. It becomes, more buoyant than the stuff around it. The motion, as the molecules are moving around a little faster, and it wants to go up. Same thing's happening on the top. So we'll write that as delta T increases, conduction, which is no motion, gives way to convection. And depending on the geometry, there can be all kinds of interesting, and the fluid, there can be all kinds of patterns of that in 3 dimensions. You get these sort of hexagonal patterns of convection cells. So if you're looking down on it, it would look like a beehive with the honey. Or you can get, and they typically are counter-rotating, right? So that, so motion would be, let's say it's rising in the middle and falling on the outside, rising in the middle and falling on the outside. So you get these different, but the patterns that they get set up in depend on the geometry and the fluid, and there's a lot of interesting stuff there. So there's a few, so this is obviously, this is a really highly nonlinear, there could be turbulence going on in here, all kinds of interesting things. And Lorenz was trying to just boil it down, right? So as opposed to the simulations I was just showing you, where you're trying to resolve, temperature and pressure and, velocity of every little pocket of fluid in there, he's thinking at a larger scale, what if we try and just predict sort of the average velocity in one of these loops, or the average temperature difference across one of these cells. So his model, his equation, so conduction, stable conduction becomes unstable as you increase this temperature difference, gives way to convection, and then chaos as the parameter gets bigger, delta T. So here's the model that Lorenz derived for this behavior. We'll just write it down, and then we'll try and understand what it means. So 3 variables, 3 parameters. The variables, we'll write down what they mean. The parameters, we'll write what they mean down. But just a few things to say. Remember, so differential equations, the concept is, x is some variable I'd like to understand the future state of. I may not be able to write down x as a function of time. There's some, set of things. But I do know how it changes. And that's what is being written on the right-hand side. So it changes not just as a function of itself, but some parameter and then another variable, y. So it's coupled. I can't just solve the x equation by itself. Often in differential equations, you have this thing and you say, oh, it looks like an exponential because the derivative of x looks like some function of x. It's a proportionality, but when it's coupled, you can't do that sort of thing usually. So then there's an equation for y. It involves x, and there's a z in here too. That's a third variable and another parameter. So these three equations, coupled system, first order differential equations, because these derivatives there's one of them. It's not the second derivative with respect to time. Okay. And this doesn't look like the Navier-Stokes equations if you've seen them before. So there's like 10 pages of derivations, which you can find in my undergraduate thesis, which I may tweet, to get from those equations all the way down to this. So there's lots of approximations and assumptions and like most of the interesting behavior being thrown out, but to try and boil down to this essence. All right, so let's write down what these things are. The 3 variables x, y, and z. Okay, so x is going to be proportional to the flow velocity. Which, if you see some of these videos, let's see. I have have other videos to show you. And they're not in either of these. Cool. Let's see. There we go. So this is a plot where you see the velocity on average inside the loop as the inset. So the simulation starts running. The warm stuff's on the bottom half. The cold stuff is on the top half. And there's some transient period where all the energy gets put in. And then it picks a direction to rotate in. This is counterclockwise to start. Pauses clockwise once. Pauses. Settles into a counterclockwise rotation. And you can see that it's this velocity in the inset. It's increased. It's now decreasing the velocity. It's increased to its peak. And then it's decreased. So it's speeding up and slowing down this fluid. But you can't quite tell by watching it. But you can still see that it's going in this counterclockwise direction the entire time. Hot stuff on the bottom, cold stuff on the top. And then there's a positive feedback happening here. The mechanism will describe what's happening. But so as it's speeding up and then now it's slowing down again, it's spending a lot of time heating up. This stuff wants to rise, so it comes up here. It cools off a little bit, and then pause. It's going to turn around and go in the other direction, just once. Okay, so what we could do, imagine doing, is taking all the little particles of fluid in the entire loop and averaging their velocities to get one number, which, let's say, if it's going in the clockwise direction, would be positive, a positive number. If it's going in the counterclockwise direction, would be negative. But on average, that of all the parts, that's the number. That's what this x is meant to represent. This variable x. So centerline velocity, the thing in the inset. That's what if you plot the x variable for the Lorenz equations and you see what it looks like, it'll look like that inset. Cool. Questions about that? This is an approximation, right? Because the velocity of all these particles, this is all different. There's a whole spectrum of velocity. Some of them are going the other way. You saw in the black light, there's stuff on the boundary, those little neutrally buoyant beads, a lot of them are going counter-rotating against the flow on the boundary and kind of sliding down and all kinds of other interesting things. But on average, this is sort of an average, this x coordinate. Questions about this? Okay. Cool. The y, so x, we'll say that positive x, so x bigger than 0, we'll say that this is clockwise. And the y variable is going to be proportional to the temperature difference across the tube, or the hula hoop, or the whatever you want to call it. It's called a thermal convection loop, but that's too many words. Or thermosiphon. That's what this is sometimes called also. They're actually used in engineering a lot, right? You want to pump. Maybe you want to heat something up, so heat up an area. So you warm water and send it through, and then it gets cooler and it wants to sink. So you want to understand the dynamics of these things so that when you're designing a heating system for a building, it doesn't, the fluid doesn't go in the wrong direction, for example. All right, proportional to the temperature difference across the tube, and typically we would just take the difference between 3 o'clock and 9 o'clock and 3 o'clock. So let's see. So in this movie, we have the temperature difference between 3 and 9 o'clock. So you measure the temperature here, and you measure the temperature here. When it's going in this clockwise direction, the temperature is going to be bigger over here because it's been warming up for a while when it gets here. And then it's cooling off for a while across the top half, so it's colder over here. And so if the temperature is bigger at 9 than 3, it's going counterclockwise, or going clockwise. If it's bigger at 3 than 9, then it would have spent some time heating in this direction, and it would be going counterclockwise. So that's the idea. And again, it's just you're measuring the temperature potentially at one spot. So when I was an undergrad doing this experiment, I just slid thermocouples into the tube, and it starts leaking. And but you can measure the temperature at those two spots, and that's probably the easiest thing to measure of all of this stuff. Velocity is hard. You got to take pictures of it and trying to identify every particle and see how much it's moved in the last unit of time, and maybe that's a three-dimensional. So it's much easier to just measure the temperature at a few places as a proxy for what's going on. So that's what the y variable will look like. It will be this temperature difference between 9 and 3, for example. Yeah. Very good. Yeah. So this delta t is a parameter, which we haven't said what its corresponding thing in here will be, but it'll be r. And as this gets bigger, you would imagine the variation in this y would get bigger, right? Because if you're putting in more energy and taking out more energy, then maybe the difference at 9 and 3 should be bigger. And you're right. So as that gets as you increase this value, you'd see lots of things are going to happen. These things happen, but also the variation in y will get bigger. Yeah. Yeah.
So in the Reynolds Number cell, is it the temperature difference
Right. You mean this, what the y variable corresponds to?
Yeah.
Yeah. So basically, it's easier to think about what y means in this thermal convection loop experiment. But yes, it's the east and west sides of one of these cells, one of these convection cells. Yeah. And this is the y variable, and y bigger than 0 will imply clockwise. So x and y are going to look alike. So when x is positive, y is going to be positive most of the time, and vice versa. And that actually is going to be what produces the two wings of the Lorenz butterfly attractor. So when we were getting ready for class, I was starting this thing out. But you end up with this. Maybe I'll show this picture first. So you get this beautiful picture where this is actually x versus z, but the fact that the x's and y's are doing the same type of thing with each other, one sort of a lagged version of the other, and the same thing's true on the other side. There's a symmetry here, and that's what produces this shape and this cool pattern. So this is a little sensitive dependence experiment where you send a little ball of initial conditions through the Lorenz equations. They're sitting up here for a particular set of parameters that we'll talk about. So there's stretching and folding going on there, obviously. That's clear. Okay, so that's the y variable, and then the z variable is going to be proportional to the deviation from a linear conduction temperature profile with height. So if we think about what the temperature is inside this chamber, if things are hot on the bottom and cold on the top, and the fluid is conducting, and there's no motion, and all of the energy is being diffused, through conduction, then the temperature should pretty much vary linearly from whatever the hot temperature is to whatever the cold temperature is as a function of height. So here's height, and here's temperature. So it's going to be near the bottom. It's going to be hot. So let's say TH and TC. It does something like that. This is the conducting temperature profile, where that difference, as you dial up the temperature difference, these two things just move away from each other. And then eventually, the conduction isn't the state that you would observe. You'd get rotation in one direction or another, and then you wouldn't have this sort of a profile. You'd get some other weird thing going on, like you get some nonlinear shape as a function of height going from top to bottom. And that'll change depending on what's going on. This function will vary with time. And so z is proportional to basically if you summed up those two areas. That's kind of what z is meant to represent. And so z is always positive. Okay, and then the time unit for this differential equation. These are non-dimensional. X, Y, and Z don't have units. In the derivation, they're non-dimensionalized, and the dimensions are stuck into these parameters, which are also non-dimensional. It all sort of cancels each other out so that you end up with meaningful parameters that if you've studied fluids before, you'll recognize some of these things. The time unit is the time for a pocket of fluid to make one trip around the loop. Which is, typically, it's on the order of 30 seconds. So in that video that I showed you with the beads, that's sped up by a factor of 10. So it would take a bead about 3 seconds in the video to make it all the way around. But so the fluid's moving a little slower than that in reality if you went and watched it. So that's the time unit to the differential equation. These are the three variables, the things that we're thinking of as changing in time. These parameters, we're going to think of them as fixed for any given experiment, but they're also things we can dial. So just like with the logistic map, we had the parameter mu that we were dialing, and we got this period doubling bifurcation, and all the attracting states started to be weird. And so that will happen here as well if you dial one of these three parameters. But yeah, we'll talk about what those are. But questions about the variables? Yeah. Yeah. Sure. Yep. And in fact, if it's going back and forth a bunch of times, it'll never make it around because it's always being pushed and pulled. But this is sort of, if it's convecting in a stable manner, one direction, it's going like this. It'll take about 30 seconds for it to go around. That's the concept. So when that's not what's going on, the time scale doesn't change. It's just that's if you're thinking about what does a 1 unit of time mean in this non-dimensional differential equation? That's what it means. Yeah. Other questions? Yeah.
So when you do that model, you didn't have it define the distance between the coplane and the top plane. How do you when you do that model? How do you define the height?
Yeah. So the question is, well, how do you decide? For a given experiment, what these parameters are, and what you would do is measure stuff. You'd measure these things. Each of these parameters relates to a different aspect of what's going on. So, for example, the geometry of the loop is stuffed into this parameter b. So if it's like this looks like a hula hoop, but you could do it with a donut. So we do simulations where the inner and outer radius are kind of equal to each other. And it looks like a donut. You get different behavior goes on there. And so in this case, it's a really thin loop, and the aspect ratio is like 30 to 1. So you end up with this distance right here, this distance, this radius being 30 times as big as that radius of the inner part of the loop. So that's a parameter. That's a choice that you make if you built the experiment, you could then measure it, or you could specifically build the experiment at a particular ratio, but that fixes a parameter like this. Some parameters you have to measure. So in that case, you fix it, and then you're going to put a fluid in. Fluid's going to have properties. Maybe you're putting air in. Maybe you're putting mercury in. Maybe you're putting, we're putting water in, and that's going to have fluid properties that are stuffed into these other parameters. Not necessarily. Yeah. So the question is, well, if you change one of these parameters, does what sorts of things happen? Everything changes if you change a parameter, right? This is a highly nonlinear system. So you end up with bifurcation diagrams in each of these three parameters, fixing the other two. Yeah. So like in the logistic map, you get this one-dimensional bifurcation diagram, but here we have three. So there's three axes along which to decide what's the stable behavior. So you get a whole parameter space of attractors. Yeah. Other questions? Yeah. Right. So in this case, I'm kind of referring to this. So this is a distance between these two. Yeah. And in the case of the loop, it's going to reflect. It's going to be reflected by this, this B that's attached to the Z here. Yeah, it's an aspect ratio thing. You have a donut where the hole on the inside is the same radius as the loop itself. Seinfeld thinks it should be called the plug because, yeah, you can buy donut holes, right, but they're the plugs that you get to eat from Dunkin'. All right, that's an aside. Other questions? Okay, so the parameters, of which we have 3. Anytime you're doing one of these modeling projects, in reality, usually parameters aren't fixed, but they're the things that change so much slower than the variables that you call them fixed anyway. Or you're going to change them in your experiment. I mean, we'll do that with this delta t. Okay, so the parameters the B parameter is related to the geometry of the experiment. And for example, in the case of the thermal convection loop, it's related to this ratio of inner to outer diameter or radius. And Lorenz, he picked in his paper, he really just looked at a few settings for each of these parameters, and he varied one of them, but predominantly kept the B value at 8/3 for his, which you shouldn't think of that as the aspect ratio. It's proportional to the aspect ratio. Okay, so that's the B parameter. We have sigma, which is the Prandtl number. And it is a dimensionless ratio of viscosity to thermal diffusivity. And it's going to measure or quantify whether and to what extent energy is transported by movement or by conduction. So particularly viscous fluids that are going to resist movement, energy is going to be moving through those fluids through conduction. So we have numbers for some examples. The examples of 0.7 for air and 7 for water and 10 to the minus 2 for mercury. Which is not a viscous fluid, and 10 to the 21 for the Earth's mantle. Prandtl, so Prandtl, which is it's a parameter that shows up in every fluid problem. And so does the final parameter, which is the Reynolds number. So that's R. And it's going to be the parameter related to this delta t that we will vary. I should have written down. Lorenz chose this to be, so I said 8/3 and 10. He chose 10 for the experiments he was doing in that first paper. Okay, so we have 1, 2. We have the Reynolds number, which is a dimensionless ratio of inertial forces to viscosity. And it's the thing, if you're in the world of fluid dynamics and turbulence and all this stuff, like Eve-Dubiev, for example, in engineering. It's the one number that characterizes how hard it is to simulate the flow that you're interested in. So typically, the bigger this number is, the harder it is to resolve what's going on. So let's see. So large R means turbulence. And at some point, people figured out initially that, this is probably 40, 50 years ago, you could, based on scaling arguments, you could build, toy models of things like planes and space shuttles and stick them in a wind tunnel. And because of the properties of fluids, if you knew the Reynolds number at the velocity you want, you could, with a scaled model, dial the flow rate just the right amount, and you could get the same types of behavior around the wings of the quarter scale model as you would, or the 10th scale model as you would in reality, but you have to just make the right adjustment of the velocity of the wind, and people figured out how to do that. And then they figured out, we can simulate them on the computer too, and they, engineers built the first plane, probably 20 years ago now, that resulted first from simulations rather than making an actual model. All right, so large R means turbulence. Typically, the R values that we see in this experiment are not so big, but I'll write down some example numbers here. So the blood in your veins is about 10 to the 3. That's the Reynolds number. When a baseball moves through the air at 100 miles an hour, it's experiencing, or the fluid attached to it, or right next to it, a Reynolds number of about 10 to the 5. And the Lorenz version of this, if you see a simulation of it, will be typically 28 is the starting value. So that's what you see up here in this. This is kind of tiny, but you can see that the number 28 has been put in here for the R parameter. Okay. Questions? Yeah. Yeah. So it's been a while since I've read the paper. I think that what happened is he didn't have enough computing power to simulate, sweeps of these parameters. But they're in the ballpark of the fluids that he was interested in modeling. So, Y28. We'll look at what happens with the bifurcation diagram for R being the one that's close. This is basically R right here, this delta T. So when R is really small, there's no motion. It's conduction. As you increase it, you get convection. As you increase it more, you get this chaotic behavior. Turns out if you make it even bigger than that, like before the fluid starts to boil, convection becomes stable again because there's so much energy going in, this thing's zipping around and it doesn't have time for this positive feedback to get it to turn around, which we haven't explained yet, but we're going to need to understand why this happens in the first place. Why does it ever turn around? Scott?
So would a higher sigma value mean that it prefers to conduct?
Yes, higher sigma means it wants to conduct. That's right, the fluid does. And it's just a property of the fluid. And if you look up Reynolds number on Wikipedia, you'll see the values of all these different things. And yeah. Other questions? Okay. All right, so let's think about what's going to happen. We're going to have, so here's the set of equations, and imagine we stuff in these three parameter values. We have to give it some initial condition, x, y, and z, and then see what happens. Now, there's no equation that says what x of t is going to be. There's only an equation for what its rate of change is going to be. So you can take a little step forward in time according to what the slope should be for a given x, y, and z. You pick up a value x, y, and z. What does x, y, and z represent? If I pick a point, x, y, and z, it represents a state of this fluid at one moment in time. So the temperature difference between here and here, that's 6. The temperature difference, from linear, maybe that's 10. And then the velocity, let's say that's 7. So those 3 numbers represent an initial condition of the, super low dimensional version of what's going on. The high dimensional version, there's obviously a lot more. But that's an initial condition. The question is, what happens to it? Does that initial condition for this parameter set settle down into conduction? Does it settle into convection? What does it do? And you use a numerical solution to a differential equation. You use a solver to do that, and there's a whole class about that. But in MATLAB, I'll send you some code that'll do this. But when you do that, you can. MATLAB has a thing in this already. If you just just open MATLAB and type Lorenz, it has an automatic thing that it does where it'll let you simulate for a random initial condition what this looks like. So you can see the blue pattern is what's being traced out by the trajectory of the differential equation. The yellow is like most recent stuff. The red dot, which you can kind of see, is the state presently. Stop. There it is right there. Okay, so this is assuming these 3 parameter values. So 8/3, 10, and 28. Pick an initial condition, let it go. What happens? You get this picture. You get this attractor. And if I pick another random initial condition and let it go again, I'll get that same picture. So on Thursday, we talked about what a chaotic attractor is. Anybody remember what a chaotic attractor is? It's kind of convoluted. We're thinking about behaviors that are not themselves periodic, but that attract states. And so you're thinking, well, I'm getting closer to some object that is itself not repeating and is chaotic. All of my initial conditions do it. If I stop this and start it again, it'll get closer and closer to the same thing, the same sort of backbone. All right, so this Lorenz attractor is a chaotic attractor. Its dimension is about 2.05, which we know from the Lyapunov exponent measurement means that as I look at adding up the 3 exponents, it's the third one that I would add, it's 3-dimensional, that gets me to be a negative sum. So I back up 1. It's 2 plus some stuff. It's 2 plus the sum of the first divided by the absolute value of the first 2. Sum of the first 2 divided by the absolute value of the third. You're going to be doing this on your homework, is measuring these exponents. And so there's a shrinking direction that's very powerful. And you can see that here. This is a little ball. It starts with a little ball, and then zoom, the ball collapses down onto a line very quickly. So there's a very strong contracting direction. And as a result, that's a very negative Lyapunov exponent and large. And that's in the denominator of this dust term that's added on to the integer 2 in its exponent calculation, which is why we end up with 2.05 for the dimension of the attractor. Incidentally, I'll tweet this website, but there's lots of other interesting things in here too, other nonlinear dynamics, sort of traditional, let's see, which one would I want to? So the Rossler attractor is another good example. This is an attractor that is largely this is like 2.0 something dimensional. Spends a lot of time down in this XY plane spinning around like a circle and then occasionally zooms out. And you're seeing a bunch of different initial conditions and what they do. So the fact that they're kind of uniformly spread out means it's sensitively dependent. That's not what I wanted. Okay. Okay, so we have MATLAB. Okay, so MATLAB, I said you could do this. Just type Lorenz and it'll do this thing, and it'll do as many as you want, apparently. I think I have it coded in here to let me edit the... How many are open? Okay. I have it coded in here to let me edit the parameter values. So if I change the value to something smaller for this R parameter, if I change the value of this R parameter, I made it small. So wherever I start, it should just settle down into the origin, because the origin's an attracting sink. Can you see it do this? Wherever I start it, it's going to just kind of settle down. So here, any initial value that I feed it is a state of the... Where is it? Oh, cool. That was fun. A state is a state of this fluid, So it could be the initial value being a random thing. It could be initialized speeding around because its velocity could be non-zero or its temperature difference. But if the parameters for that simulation say that the conducting state, which is the origin, by the way, conduction, no velocity, no temperature difference, no deviation from linear, 0, 0, 0, x, y, z. That's an attracting state for a small value of this parameter r. And so that's what you're seeing, is that any state, no matter how I start it, will just equilibrate down to nothing. And it might zoom around for a little while before it does it. There could be transient motion. And so that video would be really boring if I showed you the simulation of that, because it would just sort of move around for a while and then just come to a complete stop and everything would be green. Or you'd have the warm stuff on the bottom and the cold stuff on top. Okay, so that's if the parameter is small. And then if I change that parameter to something that's, so this says stable convection, so now this is 20. I changed it to 20. Let's get this bigger. So now that state, that origin, is now become unstable. So it shouldn't go to the origin. It's wandering around. And it's now spiraling in complex eigenvalues, spiraling in negative real part, spiraling into one of the convecting equilibriums. So the state we just watched would be, if we watched what it did, it would be, you would see that oscillation that it's going in one direction, let's say clockwise, and it's speeding up and slowing down and speeding up and slowing down, but that is dampening over time until eventually it's just constant velocity in the same direction. And that could happen on either side. It could be going clockwise or counterclockwise when it does this. Another random initial condition looks like it's going to end up going to the other, being attracted into the other one. And depending on the parameter r, the magnitude of that eigenvalue, it could be, this looks like it might be weakly attracting, because it's still going around, or it might even be outside the basin of attraction of that thing and is in the basin of the other one, and we don't know yet. It just takes a while to kick out. Can you tell? Does it look like it's getting bigger? It does to me. Oh my gosh. So another complicated thing to say about this is as the parameter grows, as r grows, even though these states are attracting, the transient period gets longer. And in fact, there's a regime of this parameter r for which some states are chaotic and some are in the basin of these two attracting convecting states. So you end up with regions of, so it's called intermittency. If you get, the trajectory could spend a lot of time looking chaotic and then dive into one of these basins, and you might not necessarily know that ahead of time. Okay, now I think it's spiraling into the convecting equilibrium counterclockwise. So now it's going in the other direction. But you wouldn't, if we were watching the experiment, and we spent an hour watching it, we wouldn't know that that was going to happen if we stopped beforehand. So it can be tricky. Questions? So here's an example of it says transient chaos is a picture from your book. That's not what I wanted. Here we go. All right, so it's spending some time going around before spiraling in. A trajectory has been plotted. B, same values, but here R is 23. When R is less than 24, there's no longer a chaotic attractor, but if it's bigger than 13, there are chaotic trajectories producing transient chaos, where it looks chaotic but then dives in. But this is now a three-dimensional state space, right? So there's volume to consider. Like, if it's an chaotic attractor, it has to attract something of non-zero measure, which means, stuff in the space that takes up volume. Okay. So the mean lifetime, people talk about how long the state lasts in a transient before heading out. And as R is chosen closer to a critical value, the number of oscillations increases, so it becomes harder to distinguish between chaos and transient chaos. This is an argument because, no simulation we've done has gone to infinite length in time. So, there's arguments that it's hard to know if something's actually chaotic. Okay, and then there's just some more details about this bifurcation process. So there's a picture, that's the conducting equilibrium at the origin. Here are these two stable convecting states, which for closer values of R to 1, which is where this bifurcation happens, they don't have an imaginary component, and things won't spiral in. They'll just zoom right in. The origin actually is largely unstable, but there is a stable manifold. So there's a saddle, and that's the thing that I'll tweet a crocheted version of. So there's the origin, this conducting state. There's a whole, ribbon of lasagna / crocheted item along. These are states of the fluid that if we got them going like that, they would all come up and balance in this conducting state. So obviously, experimentally, not at all accessible, these things, but they exist. Saddles have stable manifolds, even if they're hard to find. And they're important, right? They divide the basin. So this crocheted item that I'm talking about, that looks kind of like lasagna, it is the dividing manifold between the basin of attraction of clockwise and counterclockwise, and it has some very interesting structure to it. So you wouldn't I've drawn it looking like a plane here because I'm not good at that, but I don't know how to crochet stuff. So then, as you increase this parameter R, that is, you're making the plate on the bottom hotter, the plate on the top colder. There's a bifurcation, and the eigenvalues become imaginary, still negative real part. And then there's another bifurcation where there exists oscillations, so where we end up with the fluid basically, instead of speeding up and slowing down, it will just be in a periodic behavior. So it's basically speeding up and slowing down at the same rate indefinitely. And then that behavior bifurcates, and you get this chaotic stuff. Incredibly, there's somebody who wrote a book about this system, and it's been studied a lot. In fact, maybe I can show a video of people build mechanical analogs of this thing too. So here's an example. Because bikes are awesome, we'll do an example where they used a bike tire. So if you take a bike tire and you have the angle is effectively like this parameter R. You have there are holes in the cups. Physicists love stuff like this, right? The only thing that's not happening here is it's not in a plane that's doing sinusoidal flights up and down. But basically, you got all the ingredients are here. You got water, you got cups, they're spinning, and so the water's going out of the cups. But you can see the same type of oscillations are happening. There's speeding up and slowing down going on, and then presumably, if it's on the internet, it's going to eventually turn around, right? So it should eventually. There'll be enough stuff. These guys down here. Let me see if I can. So this cup just got a lot of water. Oh, it is going to turn around. So these are heavy, so they sink. And it's kind of. I feel like it's kind of. It could be easier to understand what's going on by looking at this for a while than the fluids, because you get a sense. This cup's going to get a ton of water, so it wants to sink, and then they're all getting a lot of. Okay, they're all getting less water when it's going really fast. So these negative and positive feedback effects, these are fighting each other. Probably easier intuitively if we sat and watched this for a while to understand why it would end up turning around. Less so for the fluid, but we got to understand that too. Let's talk about that. I think I have something to say about that. Cool. Yes? Okay. All right, so any questions right now? We're going to try and say why this happens, importantly. So this is like a little mock-up of what's going on. Some of you will know Floyd, who milled out two canals in pieces of aluminum for me for an experiment. This is sitting in my office now, this experiment. And didn't have any hair. It's kind of sad looking back on it. So what we do is we have these thermocouples that we insert at different locations to try and measure the temperature inside the fluid. And then there is like a bath or a sleeve inside here around the hula hoop inner canal that we can pump cold water into the top half here and let it out there, and warm water into the bottom half here and let it out here. And that bath, the warm bath on the bottom, cold bath on the top, drives the behavior of the fluid on the inside, which we measure with these thermocouples. So this is the hardcore experimental version of the blacklight and Home Depot tube that I was talking about before. This is data that I took as an undergrad at Bates College with the tube. So this is what the temperature difference looks like between 3 and 9 o'clock if the fluid is conducting. So it's not moving at all. It's just you get these little oscillations. You heat it up, and now it's rotating clockwise very consistently. Temperature at 9 is bigger than the temperature at 3, so it's just going constant velocity. And when I was working on this, I needed results, so I just kept turning it up and turning it up. Very, very fortunately, right before the tube melted and I came in and there was just a disaster and water all over the floor, this happened. So heated up enough, and that behavior, these equilibrium of the states that we were just talking about, they become unstable. And so instead of clockwise or counterclockwise, those push away the behavior. So it speeds up and slows down, speeds up and slows down, and then eventually switches. Speeds up and slows down and eventually switches. And here it switched for, back and forth a bunch of times. And then I don't know what the long-term bias would have been one way or the other here, because this is all the data that happened before it melted. Cool. So all right, so why does this happen? Like, this is the cool thing. Why does this happen? So I want you to imagine that the temperature difference is large enough that we're going to see this chaotic behavior. But why does that happen? We have some forces acting on the fluid. Gravity's pulling it down. We got the warm stuff wanting to rise. And I want you to imagine that it's going in this counterclockwise direction, and we end up with a pocket of fluid that arrives at point B and through some anomaly is a little warmer than its neighbors, and it wants to rise. Lots of anomalies, but so the effect that'll have is an acceleration of the fluid. If there's a little pocket there that wants to rise, it's going to speed the fluid up a little bit. And when that happens, when this fluid speeds up a little bit, it spends a little bit less time cooling. So when it gets over to the point A, it's still going in this counterclockwise direction, but because it's spent less time cooling, it's actually a little bit warmer than its neighbors still and wants to decelerate the flow of the fluid because it's still going in this direction, but warm stuff wants to rise. So it's getting over here, but it wants to, relative to its neighbors, it wants to go backwards. It doesn't. It keeps going, but it slows down and decelerates the flow. And when that happens, when it decelerates, it's then this pocket, now we're imagining it, spending more time heating than it did last time. And if it spends more time heating, it's an anomalous warm piece of, it's then a little hotter again. And so the force that it exerts to accelerate the fluid when it comes back to point B is bigger than it was last time because it spent more time warming up, which leads it to spend less time cooling off as it goes up around the top half. And when it gets over to point A, it decelerates even more, which means it spends more time heating up and less time cooling off. And if this process is amplified, eventually the fluid will just stop and turn around. So I've just told you this story about why you could see this, and that positive feedback effect doesn't exist for smaller values of this parameter. It gets damped out. So these arrows, they're sort of that I'm describing as growing. They're sort of they look kind of like random noise, but they aren't organized in this fashion. Questions about that? So this is the mechanism by which we end up with this amplified increasing amplitude oscillation. And we'll just watch this one more time. So this is actually a two-dimensional simulation. In fact, typically what we do when we make these simulations is, you can play with the parameters but still get the same type of behavior as you would in the experiment. Ideally, ultimately, we want to predict the future of the climate and the weather, and so we need good test beds to do so. We have an experiment. We have computational fluid dynamics simulations of the experiment. We want it to be like, all right, we're going to get all the parameters right, and we're going to do our best forecast we can. But in practice, when we're just doing experiments to see, what the types of behaviors are, we can do funny things like make gravity a lot smaller because it's easier to simulate. And Okay, flux, there's also the boundary. So you can decide on the boundary, do I want to impose a temperature that's fixed, that's cold on the top and warm on the bottom? That's what I've been saying all along. In practice, sometimes for the CFD, it's easier to make the energy transferred through the top half or into the bottom and out of the top half, to make that energy fixed. Practically speaking, it's probably a mix of these two things. Like in the experiment, there's no way I can keep the boundary of the wall the same exact temperature all the time, because sometimes hot stuff's running through it, sometimes cold stuff's running through it. There's no way you can make the boundary exactly the same temperature. But maybe you can figure out how to get the energy moving through it to be close to constant, which is what that heating tape I was describing that melted my experiment was trying to do. It was trying to give a constant amount of energy to the bottom half. So that's called the flux boundary condition, this one. That's the amount of energy being pulled out of the top and put into the bottom. So really interesting things. You get these little sort of Kelvin-Helmholtz waves that happen right near the thermal discontinuity as things are changing from one direction to another, when the temperature differences are starting to grow. We tried to figure out why the wavelengths of those were what they were. And yeah, so this is now so this is the x variable if we were plotting what's going on here. The attractor, okay, so yes, I have other things to, what was I going to show you? There, that was it. So here is the mass flow rate is one of the things you measure. Like take one of those cross sections, how much stuff's moving through it. That's a proxy for velocity. And I mentioned earlier, maybe it's a few weeks ago now, that we do this state reconstruction. When it's hard to measure more than one thing in an experiment, you can plot a delayed version of that variable against itself. So here's what happens when you plot this mass flow rate against what it used to look like. And so you get this. This is not what the Lorenz attractor looks like if we plotted x and y, for example, velocity and temperature difference. But the properties are going to be the same, like the dimensions of the attractor that you get back. And it's very cool. These red dashes are the values of the convecting equilibrium that is pushing this state away. So when you saw the Lorenz attractor animation earlier, it's basically tracing out the full three-dimensional version of this picture on the right. This picture is just being made by plotting this time series against an older version of itself. So it's pretty amazing what you can do with that technique. Questions? Yeah.
Way to tell when you use that and when you can't. Obviously, it works because of correlation.
Right. Because in our case, x and y are very similar to each other. The properties are, yeah.
Right. Is there a way you can tell that just by doing it, I guess?
Yes. So what would happen if it wasn't working is that this would look like y equals x. And, or it would look like just noise. I'll show you, so Lorenz did something related to this that I'll show you next time we talk about it. It's pretty cool, actually. Yeah. Relating back to the tent map, he figured out how to make this look like a tent map. It's pretty awesome. Other questions? Yeah.
What happens if your initial conditions are in the middle of the holes in Lorenz attractor?
So those holes are, for smaller values of the parameter, attracting regions for the convecting states going clockwise or counterclockwise. So there are unstable equilibrium points in there. And if you start near there, they'll just get pushed away and go into the other, go and do what everything else does. Yeah. So office hours tomorrow, 9 a.m. Work on your homework.